this video, we're going to look at acid-base properties of salts. Salts are really just ionic compounds, and if you think of what ionic compounds are made of, they're made of ions. A lot of people have this misconception that anytime you see a salt, an ionic compound, like it would be neutral in solution, whether it's NaCl, KCl, CuCl. Anytime they see a salt, they say it's neutral, but that's actually not the case. Some salts are neutral, some salts are acidic, and some salts are basic. And it's actually all going to come down to which ions make up that salt. So let's investigate this a little bit further. So if you remember that the relationship between Ka and Kb for a conjugate acid-base pair is that Ka times Kb is Kw. What does that mean? That means that the stronger something is as an acid, right, the larger the Ka, that means the smaller the Kb and therefore the weaker the base. This is an inverse relationship, and the product is always equal to a constant, which is 1 times 10 to the negative 14 at 25 degrees Celsius. Might be a different value at a different temperature. If we think of a strong acid, like make sure you know your strong acids, nitric, sulfuric, perchloric, OMI, HCl, HBr, and HI. HCl, if I look at the Ka, it's 1.3 times 10 to the 6th. It's a very large Ka. Ka is bigger than 1 all the time for a strong acid. That's because it 100% ionizes and it really favors the product, so much so that we say it goes to completion. If I write the conjugate base for HCl, this is where the idea of an ion is going to come in. What is the conjugate base of HCl? If I make this act as an acid, it releases an H+. The conjugate base is Cl-. If I were to calculate the Kb for Cl- using this equation, I would get that the Kb is 7.7 times 10 to the negative 21. Look at how small that number is because the Ka is so large. So what you're going to notice is if you have an ion that is actually the conjugate of a strong acid, then it's going to have negligible strength as a base. Its Kb is going to be so small that it's not going to be able to function as a base in solution. What does this mean if I show like a particulate diagram? That means if I have HCl and it acts as an acid, meaning it ionizes into H+ and Cl-, this Cl- is going to have such negligible strength as a base that it cannot accept an H+. That's the definition of a Bronsted-Lowry base. So it remains as H+ and Cl-. It's unable to go backwards, and that's why we always put this one arrow pointed to the right to show 100% ionization of a strong acid. So again, the lesson here is that if I have an ion that is the conjugate base of a strong acid, it's going to have negligible strength and it's not going to influence the pH, and that would contribute to a neutral pH. So if I have, let's see, a different scenario. If I have a weak acid like HF, okay, if I look up the Ka, here is 6.8 times 10 to the negative 4. It's less than 1, but it can still function as an acid. It's just not 100% going to ionize. Let's write the conjugate of this weak acid. Notice it's an ion. What is salt made out of? Salts are made out of ions. So again, this is where the idea of a salt being acidic, basic, or neutral is going to start coming into play. If I were to calculate the Kb for this using this equation above, I would find that the Kb is 1.5 times 10 to the negative 11. Okay, it's not going to be a strong base, but what you're going to notice is if you have a conjugate of a weak acid, it's going to have some weak strength to it as well. We've done weak base problems where the Kb is around that scale. And if I'm showing this in a particular diagram, what this means is if as the HF ionizes into H+ and F- as it acts as an acid, that F- is going to be able to act as a base. It is going to be able to accept some H+ and turn back into HF. And again, that's why we write these reversible arrows like this. That's why it's an equilibrium condition. So what's the moral here? Hey, if you have an ion in solution and it's the conjugate of something weak, then that ion is going to be able to function as an acid or base. And it will affect the pH, and it will be acidic or basic. Like in this situation, F- will be able to act as a base. So if you have F- in solution, you're going to have a pH greater than 7. You're going to have possibly a basic salt. So again, what you're going to notice is once you identify the ions in your salt, it's going to be really helpful to think about what acid or base did that salt come from. So like Cl-, that's the conjugate of what acid? Of HCl, which has, I know, really high strength. So that Cl- is going to have really low strength. So again, the ion in a salt might be acidic or basic only if it's the conjugate of a weak acid or base, because then that thing can be weak. So if I kind of show you this chart, all my strong acids here, okay, look at them at the top, HCl, H2SO4, those are my strong acids. Their conjugate bases are of negligible strength. And same thing on the bottom. Here's some strong bases. Their conjugate acids, again, are of negligible strength. But I have this sweet spot in here where if I have a weak acid, its conjugate base will also be of weak strength. And that is when the ion will be acidic or basic. An ion will be acidic or basic only if it's the conjugate of a weak acid or base. Okay, so if you think about this, if I'm thinking about my anions, and so if a salt has a cation and an anion, right, a positive ion and a negative ion. If it's the conjugate of if you're looking at your anion, anions means negative ion, in case you didn't know. If it's a conjugate of a strong acid, then it will have negligible strength, and the solution will end up being neutral. That ion will not be able to function as an acid or base. However, if your anion is a conjugate of a weak acid, it will then have weak strength and it will be basic. Take a moment, try this example, and figure out of these ions, these negative ions, which might be neutral, which might be basic. Okay, so it's helpful to think about what its conjugate is. So Br minus is coming from HBr. That's the conjugate acid. So that Br minus would not be able to function as anything in solution as an acid or base. It would create a neutral solution. Okay, this is the acetate ion. Its conjugate acid is acetic acid. So this would actually be able to function as a base in solution because this is a weak acid, so its conjugate is a weak base. Simple. NO3 minus, that's the conjugate of a strong acid, HNO3, so this would be a neutral ion. It will not give a lower pH than 7 or a higher pH than 7 if we're at 25 degrees Celsius. And BrO3 minus is the conjugate of bromic acid, which is not a strong acid, so this is a weak acid. This would then have a weak strength as a basic ion. So notice that the negative ion will either be neutral if it's the conjugate of a strong acid, otherwise it will be basic if it's the conjugate of a weak acid. Now cations are going to be essentially the opposite. So the cation, its conjugate would be a base. So if a conjugate of a strong base, that cation is going to have negligible strength and be neutral. Just like the same reasoning as the acid. If you have a very large Kb for a base, its conjugate ion is going to have negligible strength. If it's the conjugate of a weak base, it will have weak strength, and that cation would be acidic. Take a moment and try this example, and then check your work. NH4+, think about what base that made that, okay, or what's the conjugate base to this. So if I make this act as an acid, donate an H+, turns into NH3, that's the base. This is a weak base, so this would also have weak strength as an acid. K+, its conjugate is KOH. At first glance, you might be like, hey, how can this positive ion what's the conjugate of that? How do I make it accept an H plus or donate an H plus? If you think of your bases that actually have an OH minus attached, when those ionize in water, those you can actually make like KOH releasing K plus and OH minus. So technically, K plus is the conjugate acid of KOH. I don't have to technically even do the Bronsted-Lowry definition of making it accept an H plus or donate an H plus. I can kind of just use the ionization of KOH. And this is how you get those positive ions perhaps functioning as something acidic in solution, only if their conjugates are not strong bases, only if their conjugates are weak bases. So K plus, if I think about the base that comes from, it comes from KOH, that's a strong base, so this K plus would have negligible strength as a base, as an acid, and therefore this would be a neutral solution. K plus would have no functionality as a base. Ca2 plus, if I think about where that came from, that's essentially the conjugate of calcium hydroxide. That's where that Ca2 plus came from. And this calcium hydroxide is a strong base, so its conjugate Ca2 plus would be of negligible strength. This again would be neutral. Cu2 plus, its conjugate would be copper 2 hydroxide, which is not a strong base. Make sure you memorize your strong bases, group 1 in Cabasser. So this would be a weak base, so Cu2 plus would be able to function as a weak acid in solution. So notice again the takeaway here is if you have a positive ion solution, it would be neutral if it's the conjugate of a strong base. Otherwise, that positive ion can be acidic if it's the conjugate of a weak base. So notice it's really only the conjugates of things that are weak that are functioning as acids and bases in solution. The anion and the negative ion could be basic if its conjugate acid is a weak acid. The cation could be acidic if its conjugate base is weak. So now when you're looking at salts and you keep all this in mind, it's helpful to think about, well, what acid and base combine to create that salt? So remember if you just think of an acid-base reaction, an acid plus base are typically reacting to form water and a salt. So your salt will have a positive and negative ion. Think about what acid and base made that. Anytime you have something derived from a strong acid and strong base, your salt is going to be neutral because remember, neither of these ions can function as an acid base in solution that have negligible strength. So for instance, NaCl. What made NaCl? Okay, well the Na had to have come from NaOH and the Cl had to have come from HCl. NaOH plus HCl would make H2O plus NaCl. That would be the salt. So this is strong base and strong acid. Okay, this salt is neutral. Neither of these ions would have any strength. They'd have negligible strength as acids or bases. Calcium nitrate, okay, what acid and base combined to make this salt? This came from calcium hydroxide. NO3 came from nitric acid. Those are both strong, so this would be a neutral salt. So NaCl, calcium nitrate would be neutral salts. Their ions are all the conjugates of something strong. Now, if you have a different combination, if you have a strong base and a weak acid, salts derived from that are going to be basic, and let's look at why. So something like NaClO, what acid and base combine to make that? That would be coming from NaOH, okay, that's a strong base, and ClO minus would come from HClO. Oh, wait a minute, that is a weak acid. So it's actually this hypochlorite ion, the ClO minus, that can function in solution as a base because it's the conjugate of something weak. So it's the ClO minus which is going to make the solution have a basic pH or a pH greater than 7 at 25 degrees Celsius. If you look at this example here, okay, this Ba came from barium hydroxide, which is a strong base. Okay, this acetate ion came from acetic acid, that's a weak acid. So this acetate ion can actually function as a base in solution because it's the conjugate of something weak. And if you have salts derived from weak base and strong acids, then those are going to be acidic. And if we think about this, okay, NH4Cl. Okay, NH4, what base is that coming from? That's really coming from ammonia. Cl is coming from HCl. HCl is a strong acid, so Cl would be negligible strength, but NH3 is a weak base, so NH4 plus would have some strength as an acid, and that would make the solution acidic. That's why NH4Cl would be an acidic salt. Okay, and same thing here, magnesium would come from magnesium hydroxide. Oh, wait a minute, that is a weak base, so the Mg2 plus ion would have some strength as an acid. This would be an acidic salt. Okay, so again, notice it's actually the ion that's coming from the weak acid or base that's functioning as the conjugate base or acid in solution. Take a moment, try this example. Tell me whether these salts are acidic, basic, or neutral. It might be helpful to think back to which acid and base created them. And then also determine which ion is responsible for the acidic or basic pH, if that's the case. Okay, so look at this first one. This is coming from NH4, is coming from ammonium. Ammonium is coming from ammonia. For each of these, I'm going to pause the video, try it first, determine if they're acidic, basic, or neutral, and then tell me which ion in the salt is actually responsible for the pH being acidic or basic, if it is one of those two. So for number 1, NH4NO3, let's figure out what acid and base made that. That must have come from NH3 and HNO3. NH4 plus is the conjugate of the weak base, so that would be slightly acidic in solution. NO3 minus is the conjugate of the strong acid, so that would have negligible strength. So this would actually be an acidic salt because it's the NH4 plus, the conjugate of the weak species, that can act as an acid in solution. Okay. Number 2, these are coming from strong acid and strong base, so both ions would be neutral in solution. They would not be able to function as acids or bases. They would have negligible strength. Number 3, the acid and base that would make this, okay, we have iron 2 hydroxide as a weak base. SO4 would be coming from a strong acid, so it's the conjugate of the weak species, the Fe2 plus, that can function, and in this case it would function as an acid because it's the conjugate of a weak base. KCN comes from KOH and HCN. KOH is a strong base, so K plus would not be contributing to any type of pH. HCN is a weak acid, so its conjugate CN minus would be able to function as a base, so this would be a basic salt due to the CN minus ion. That would be able to act as a weak base in solution. Calcium perchlorate, calcium hydroxide is a strong base, perchloric acid is a strong acid, so this would be a neutral salt. Neither ion would be able to function as an acid or base. The pH would be neutral. pH would be 7 if it were at 25 degrees Celsius. And the last, NaOH is a source of Na plus in this situation, and that's a strong base, so this would be a neutral part of the salt, and phosphoric acid is a weak acid, so PO4 minus would also be weak. It would be able to function as a weak base, so this would be a basic salt. Now that you know how to figure out which ions act as an acid or base when you're dealing with a salt, we can actually show that ion acting as an acid or base in a reaction. So for instance, something like Cn minus, we can show it acting as a base. If you remember, you might say, hey, wait a minute, bases release OH minus, Cn minus doesn't actually have an OH in it. How do I get it to show a release of OH minus? You're actually making it react with water. So whenever you're showing these ions functioning as acids or bases, you're really making it just react with water. And it's the water that turns into hydroxide or hydronium, H+, and that's how you get something acting as either an acid or base. And a fancy way of saying this reaction with water is hydrolysis. So if you remember, the anion of, that's a conjugate of a weak acid, is going to be able to function as a base in solution. So if you have, let's say, the acetate ion, that's, the conjugate of acetic acid, which is a weak acid, so this can function as a weak base in solution. How do I show it acting as a base? Just make it react with water. If this is acting as a base, it'll accept an H from the water and turn into its conjugate acid, acetic acid. And H2O would be acting as an acid. It would donate an H+ and turn into hydroxide. That's how you get hydroxide in solution. That's how you get this acting as a base. And this should look really familiar because we've been writing ionization reactions for acids and bases before. You're just finding the ion that's acting as a base in this situation and making it react with water to show it acting as a base. Now, if you have a conjugate of a weak base, okay, that's going to act acidic in water. So if you have something like this example here, this is going to act as an acid. It'll donate an H+, and it'll turn into its conjugate base when it does that. This is a weak base, notice, and that's why this can function as a weak acid. And water, by, accepting an H+, turns into hydronium, and that's how you get this acting as a weak base in, a weak acid in solution. You have this presence of hydronium. Now, if you have an H in your actual formula for your acid, it's simple enough to actually just take that acid and show it releasing H+ and turning into its conjugate base. That's usually the way that you'll see me do it as well. Why? Because these two reactions are really interchangeable. Whether I make it react with water or not, if I was going to write the Ka expression, water would drop out because it's a liquid, and H+ and H3O+ are interchangeable, so I'd get the same Ka expression. And that's why, if you remember, when we were doing weak acid problems and I said show the ionization, we would really just show the ionizable H coming off and turning into its conjugate base. Remember that any cation, except the alkali metals or Cabasser, because those are conjugates of strong bases, is going to be able to function as an acid in solution. Now you might ask yourself, hey, wait a minute, there is no H+ in this, in this formula. So how do I show it acting as an acid? What actually happens is this reacts with water, and this ion, in this case Cu, is going to get attached to OH. It turns into the hydroxide, which is a weak base, and that's why Cu plus can function as a weak acid in solution. And then you also get this release of H plus, and that's why this acts as an acid. Okay, and as a reminder, there are some anions that are amphoteric that can act as acids or bases. But again, this process is just called hydrolysis, showing the ion ionize essentially and act as an acid or base in solution. Once you write these hydrolysis equations, and you might have to use them in a problem, usually they don't give you the correct K that you need. And what I mean that is they'll give you the K for its conjugate. So if I'm doing a reaction with the part of the salt acetate ion, they might give me Ka for acetic acid. And it's just a heads up to make sure that you convert into the K that you need. If I'm looking at a reaction of the acetate ion reacting with water to create OH minus, it's acting as a base, then I need to get the Kb for this problem. I don't want to use the Ka. And I use that fact that Ka times Kb equals Kw. And we'll see this in a moment. Okay. The other question that you might ask yourself is, hey, we've looked at everything where one thing is coming from something strong and the other is coming from something weak. What if you have a salt that's coming from a weak acid, one part, and the other part's coming from a weak base? In that situation, you're going to have to look up Ka and Kb values, and whichever ion has the largest K, that's going to control the pH. So what do I mean by that? So if I have NH4F, right? NH4 plus is the conjugate of weak base NH3, so this is slightly acidic. F minus is the conjugate of weak acid HF, so F minus can be slightly basic. So how do I know if this is going to end up raising or lowering the pH? Which is going to win out, the acidic or the basic? So I could look up Ka's and Kb's. The Ka for NH4 plus is here, 5.6 times 10 to the negative 10, and the Kb for F minus, 1.5 times 10 to the negative 11. And just make sure you have the right thing. I do have the Kb for F minus, which is acting as a base. I do have the Ka for NH4 plus, which is acting as an acid. So what's larger here? Okay, NH4 plus has a larger K than F minus. So the solution is going to be slightly acidic. Okay, so even though F minus can act as a base, NH4 plus is a stronger acid, so it would end up lowering the pH. This would be an acidic salt, the combination of these two things. Okay, now you know how to figure out if a salt's acidic or basic. You can now do problems that are just like weak acid and weak base problems, but with salts. So you might see an example, what's the pH of a 0.3 molar NaF solution? And here I give you the Ka for HF. So here is my solution, NaF. Let's figure out, is this going to function as an acid, a base, or be neutral? So NaF is coming from NaOH and HF. Right? NaOH is a strong base, HF is a weak acid, so the conjugate of a weak acid, F minus, would be able to function as a weak base. So F minus is going to create a slightly basic solution. F minus is going to be the thing that's going to function as my base. So let's write an ionization equation, or the hydrolysis of F minus. If it's a base, I'm going to make it react with water. Okay, F minus will pick up an H, acting as a base. H2O would turn into OH minus, acting as an acid. And now I have a reaction of an acid. I have the reaction of a base. I have an initial concentration. I want a pH. This is just going to be like any other weak base problem we've done before. The only thing is do I have a Kb? No. I have a Ka. So just make sure before doing the problem that you change your Ka into Kb, since this is a problem involving a base, F minus. Now also this is a monohydroxy weak base problem, right? There's one OH minus released. Okay. If I get my Kb, I get that I have 1.4 times 10 to the negative 11. So I can use that 5% rule, right? The difference between my initial base and my Kb is way more than 10 to the third or 1,000 times difference. So I can either use an icebox with that 5% rule, or I can even use this shortcut equation that we remember from weak bases, and there's a video on that if you need to go back to it. I have my Kb now, I have my initial base, and I can solve for my OH minus. So let's do this shortcut. So plugging in, I get my OH minus is 2.1 times 10 to the negative 6. I can get the POH by doing the negative log of this number. I get 5.69. And if I subtract that from 14, I get my pH. And there's my problem. If you wanted to, you could have done this with an icebox instead. Okay, so here's my equation. I don't need the water because it's not in my equilibrium expression. Put my initials, put in my changes. Okay, I can assume that due to my 5% rule, which we said would apply, that x is going to be so much smaller than 0.3 that this is just 0.3x and x. And again, if you need more help with this type of problem, go back to my other videos. Now I can plug into Kb. Make sure you've converted your Ka into Kb because this is a base problem. Okay, and if I plug in, I get the same answer as before for my OH minus. I get the same answer